Right, we're going to look at a different kind of problem with solids of revolution. This is one with a little bit of a trick. Okay, so if we have a look at worked example 9.22, you'll see we have this shaded region that's rotated around the x-axis, right? But the difference between this and a usual solid of revolution is we have this gap, all right, between the x-axis and the shaded region. Okay, so if you have a look at the diagram that I've drawn, right, and it really does help to draw yourselves accurate diagrams because it helps you to visualize what's going on. Okay, you can see what's happened is as this thing has rotated around the x-axis, it's created a space in the center, right? This space, because of the way the shape has been given, has caused a cylinder to be in the center of this volume. Okay, so we need to come up with a slightly modified technique in order to work out the volume of just the shaded region. Okay, if we took the boundaries as is from 0 to 2, right, of our equation, it would work out the volume for the entire rotation, right? It would fill, if you want to say, up the center as well. But we can use that to our advantage. Okay, so what we can say is if we work out the volume of the whole piece and we subtract the cylinder volume on the center, that will give me the shaded region. So this is very similar to when you were working out area between two curves, right? You would take the area of the top function and you would subtract the area beneath the bottom function, and that would give you the area between the two. Okay, now when it comes to volume, we just have to be very careful, right? So we will discuss that as we get there, right? So having a look at our question here, we want to find the volume of the shaded region rotated through 360 degrees about the x-axis, right? We have the curve 2x squared plus y squared equal to 9. Okay, so we're going to start off by working out the volume and pretending that we're not interested in the portion underneath the graph. Okay, we're just going to work out the volume as is. So we're going to say that the volume is equal to, right, now we just need to state our which one of our two volume formulas we're using. We're rotating around the x-axis, so this is going to be the integral from a to b pi. Y is going to give me my radius squared with a little bit of change in x. Okay, so that is the volume from the x-axis all the way underneath the curve. Okay, but we don't want the whole volume. We want to take away that tiny portion of volume, right, below the y equal to 1 line. So this line here is just the y equal to 1 line, right, given by coordinate p, right? Now this creates a perfect cylinder, all right, which we could just use the formula for the area of a cylinder in order to work that out. So we're going to do it like that the first way, and then I'm going to show you a different method, because we're not always going to get a perfectly cylindrical shape as the center volume, all right? It might be another curve or a line with a different equation. So it might even help to think about this as a separate volume altogether and integrate it separately. So I'm actually just going to write, take away the integral from a to b of pi y squared dx, right? So we're going to obviously have two different y's here. They're not going to be the same, all right? So let's put the values into the equation, right? We're going to have the integral from, right, our lower bound is going to be 0 from the x-axis all the way up to 2 on the curve. Now we want pi, we want y squared. Now I've manipulated the equation over here to show me that y squared is just going to give me 9 minus 2x squared. So this will just be 9 minus 2x squared with respect to x. And we're going to take away that empty volume that we don't want in the middle. This is also from 0 to 2 pi. Right, now we have to think, what is y squared in this situation? Okay, so we need to look at the line under which we're trying to find the volume. And that line, as we said before, is just the line y equal to 1. So y squared is just going to be 1 squared. And the width is going to be that tiny change in x. Okay, so now we have two primitive functions to anti-differentiate. Now, a word of caution, all right? When we learnt about area, we said, well, if we have two integrals that are being evaluated between the same limits, we can combine the functions, right? Now, I'm going to caution you not to do that with volume because it can cause problems, which I'll show you at the end of this video. All right. So let's just integrate these things separately for now, and you'll see at the end why we have to we can combine them. We just have to be very careful with the way that we do it. It's not as easy as with the area, right? So let's anti-differentiate these. I'm going to pull pi out because it's a constant, which we don't need to worry about. Okay, this is going to give me we need to anti-differentiate now, so we're going to get 9x take away, right, x cubed squared is going to become x cubed on 3, and I want this from 0 to 2, and I'm going to be taking away, right, again I'm going to pull pi out the front there. We're going to anti-differentiate 1 squared, which is just going to become x, and this is from 0 to 2. So let's now put in our values into our primitive function. So what we're saying is we want pi f of 2 take away f of 0, take away again pi, and in this function f of 2 take away f of 0. I'm just using f as a placeholder. Okay, it's just to explain that you understand what you're doing by putting in the boundaries into your primitive function to find those volumes. All right, so we just have 2 to work with now. So we're just going to use lots of brackets to keep track of our numbers. We have that pi out the front. Okay, and in the first bracket we're going to have 9 times 2 minus 2 cubed all over 3, and you can see that we're going to be taking away 0. There's my first one, and we are taking away from this again. Let's not forget about pi in the front there. We're just going to have 2, right, take away 0. Right, we have pi in both of them, so combining them together, we're going to have pi, right? In the first bracket, we're going to have 9 times 2, which is 18, take away 16 over 3, right? So we can go 18 take away 16 over 3. That's going to give me 38 over 3, and we are taking away 2, and this is going to leave me with 32 pi over 3. Okay, so that gives you the volume just of, if you look at my graph, the shaded region. Okay, it's we've taken the volume, we've pretended that we've taken the entire volume. So if I had to draw that, I would say what I'm doing is I'm first taking the volume of the whole thing, okay, and then I am subtracting that volume for the center, and that gives me the gray area. Okay, so let's talk about why we have to be careful, right? When we're combining these two functions, why we have to be careful right? If we just want to combine them like we did with area. Okay, so I'm going to rewrite this here. We have the integral from a to b of pi. Right, now I'm going to give my function just a random name, and I'm going to say, assume this function was the function a, and it's a squared, right? And this is with respect to x, and we're taking away the integral from a to b of pi, and let's call my second function b squared with respect to x. Again, I'm just making up names. These functions could be anything, right? Now, when we combined them with area, we had the assumption that we could just go the integral from a to b of pi, and let's just go a minus b squared with respect to x, right? Because we're just subtracting the equations. Now, let's have a look. When we expand this out, what are we going to get? Well, we're going to get a squared take away 2ab plus b squared. And that definitely isn't a squared minus b squared. Okay, so if you want to combine the volumes, the correct way to do it is like this. The integral from a to b of pi, right? We can have in brackets, but it's a squared take away b squared with respect to x. Okay, so when we're dealing with volumes, it's not like area. We just have to be careful, all right? And if you're worried you're going to mess it up, then what I would suggest you do is just evaluate the integrals separately, right? Calculate the volume of the entire portion of the thing that you're trying to work out, and then subtract the inner volume to find the volume that the shaded region encloses. Okay, so hopefully that will help you with some of these questions where the area you're being asked to work out is not actually touching or is not bound by either one of the two axes, right? And if you think about it, that's just going to create a hollow shape on the inside.